you are here. Those two words and a tiny pulsing blue dot on a screen, and all of a sudden you're not lost anymore. But have you ever actually stopped to wonder how? How does that little blue dot know exactly where you are with such spooky precision? There are no wires connecting you to anything, no visible beams shooting down from the sky. It feels like magic, but it's not. It's actually a massive invisible system working silently all around you 24/7. It's a constellation of 31 satellites hurtling through space at thousands of miles per hour. It's a little-known network of ground stations scattered across every single continent. And of course, it's the phone in your hand. All three parts are working together in perfect, mind-blowing sync. Today, we're pulling back the curtain on this global machine to reveal the three hidden segments of the Global Positioning System, or GPS, that work together to track your every move. The story of your location begins far, far from home, about 20,200 kilometers, or 12,550 miles straight up. In that cold, silent vacuum, a fleet of 31 satellites known as the space segment is in constant motion. These are the bedrock of the entire GPS network, arranged in 6 distinct orbits to make sure that from almost anywhere on Earth, at least 4 of them are in your sky at all times. So don't think of them as spies, think of them as celestial lighthouses. For centuries, sailors navigated by the stars, which were fixed points in the night sky. GPS satellites are our modern-day constellations, but with a wild difference. They are constantly moving, circling the entire globe twice a day at a breezy 14,000 kilometers per hour. So, how do you navigate by something that's always on the move? It's because each of these satellites is relentlessly broadcasting a very simple but vital message. Over and over, each satellite just shouts out two key things: its exact position in space and the exact time the signal was sent. And this timekeeping isn't just good, it's almost perfect. Every satellite carries multiple atomic clocks on board, devices so fantastically precise they might lose a single second every few million years. This constant stream of information from the satellite saying, "I am satellite X, I am right here, and the time is now," is the first critical piece of the puzzle. It's a signal that travels at the speed of light, carrying the seed of your location down to Earth, just waiting for something to catch it. That something, as you've probably guessed, is the phone in your pocket, the watch on your wrist, or the dashboard in your car. This is the user segment. Billions of GPS receivers built into the gadgets we use every day. Your receiver is basically a professional listener. It's constantly scanning the sky, listening for the faint whispers of those satellite lighthouses. At any given moment, your phone is probably hearing from 6, maybe even 10 or 12 satellites at once. When your receiver picks up a signal, it notes the exact time it arrived. And this is where the real trick begins. The receiver looks at the timestamp in the satellite's message, the time the signal was sent, and compares it to its own clock when the signal was received. Because the signal, which travels at the speed of light, a known constant, the receiver does a quick calculation. Distance equals speed multiplied by time. It then figures out how long the signal took to get there, and, just like that, it knows its exact distance from that one satellite. But knowing you're, say, 20,000 kilometers away from a single satellite isn't super helpful. That just means you're somewhere on the surface of a gigantic imaginary sphere around that satellite. So your receiver listens to a second satellite. It does the same math and figures out it's, for instance, 22,000 kilometers from that one. Now you have two giant spheres, and where they intersect creates a perfect circle. You've narrowed your position down from anywhere on a sphere to somewhere on a circle. Getting closer, but still not a blue dot. This is where the third satellite comes in. Your receiver measures its distance to a third one, creating a third sphere. The spot where all three of these spheres cross is your location. This geometric game of find the intersection is called trilateration. With just 3 signals, the system can figure out your latitude and longitude, your 2D position on the planet. It's an incredibly elegant solution to a problem we've had for ages. And if you're enjoying this, maybe take a second to subscribe and hit that notification bell. We explore amazing science and the hows and whys that shape our world every week, and you won't want to miss what we have coming up. But there's a problem. For this whole thing to work, the timing has to be absolutely, flawlessly perfect. Light travels at nearly 300,000 kilometers per second. If a satellite's clock is off by just 1 millionth of a second, your location would be off by almost 300 meters, or about 984 feet. If the clocks were off by a mere millisecond, you'd think you were hundreds of kilometers from where you actually are. Your map app would be completely useless. The atomic clocks on the satellites are incredible, but they're not totally immune to the laws of the universe. They are moving at insane speeds and are in a different gravitational field than we are down here. And this is where it gets truly mind-bending. For GPS to work at all, it has to account for Albert Einstein's theory of relativity. Seriously, special relativity says that because the satellites are moving so fast, their clocks should actually tick about 7 microseconds slower every day than ours. But at the same time, general relativity says that because the satellites are in a weaker gravitational field, their clocks should tick about 45 microseconds faster every day. You combine the two effects, and to us on Earth, the satellite clocks look like they're running fast by about 38 microseconds every single day. An error of 38,000 nanoseconds would be a catastrophe, causing a navigation error of over 10 kilometers a day. The whole system would collapse in hours. This is why the third and most secretive part of the system is so crucial: the control segment. This is a network of ground-based monitor stations, master control stations, and antennas spread across the globe. These stations are the silent guardians of the whole system. They constantly track the satellites, monitoring their health, their exact flight path, and most importantly, the ticking of their atomic clocks. The master control station analyzes any tiny drifts and calculates the exact corrections needed to account for those relativistic effects. It then beams those corrections back up to the satellites, basically telling them to adjust their clocks and their position data. This ensures the message they send down to you is as close to perfect as humanly and physically possible. So we have the space segment broadcasting signals, the user segment listening in, and the control segment keeping everything in perfect time. 3 satellites give you your spot on the map. But there's one final genius-level twist. The atomic clocks in space are nearly perfect, and the control stations make sure they stay that way. But what about the clock in your phone? It's a cheap, mass-produced quartz clock, not a multi-million-dollar atomic one. It has errors, big ones. In the world of GPS, your phone's clock is hopelessly inaccurate. This timing error in your own device is the final variable that has to be solved, and the solution is the 4th satellite. Think about it. Your phone needs to solve for 4 unknowns: latitude, longitude, altitude, and the precise actual time. And to solve for 4 unknowns, you need 4 equations. So your receiver needs a signal from a 4th satellite. Your phone's software knows its own internal clock is junk. It uses the signal from that 4th satellite as a perfect reference point to calculate the exact error of its own clock, and then it corrects for it instantly. By solving for its own time error, it synchronizes itself with the hyper-accurate time of the entire GPS network. This is why a true GPS lock requires at least 4 satellites. 3 give you a position, but it's a shaky one. The 4th one gives you precision. It's the final piece of the puzzle that turns a rough guess into that steady, reliable blue dot on the map. So, the next time you pull out your phone to find the nearest coffee shop, just take a second to appreciate what's happening. At least 4 satellites, over 20,000 kilometers away, are sending signals timed by atomic clocks that are being corrected for Einstein's theory of relativity. And a hidden network of ground stations constantly choreographing this celestial dance. And the little supercomputer in your pocket is catching these faint signals, calculating your distance from each one, and using a 4th signal just to figure out what time it really is, all in a matter of seconds. The 3 segments, space, control, and user, are working together in a constant, invisible symphony of physics and engineering. And this system has done so much more than just help us not get lost. GPS is essential for air traffic control, preventing mid-air collisions. It guides tractors in fields to increase crop yields. It synchronizes global financial markets and power grids. Emergency services use it to find people in trouble, and scientists use it to monitor earthquakes. From global shipping and drone deliveries to even playing games on your phone, this invisible utility has become the backbone of modern life. All of it made possible by that little blue dot, a simple representation of one of the most complex and brilliant technologies humanity has ever created. If you enjoyed this look into the tech that runs our world, please give this video a like and don't forget to subscribe for more. We'll see you in the next one.